All right, guys, let's give it a chance here. Let's see what we can do. I want to do this video for NMR, IR, Index of Hydrogen Deficiency. Get a little review about how to do this. I got a little chicken down here that's bothering me over by my feet. He doesn't want me to pick him up, but he may jump up and give us a little bit of a problem. You see that little tail right there. This little chicken might come up and bug us, but let's see if we can get him to settle down, and we'll do a little bit of work with some NMR, IR, and Index of Hydrogen Deficiency. Let's see if I can get through it. I'm going to try to pop back and forth between a lot of different things, and so it might get a little bit head spinny with all the different movement between one thing and another. And so I apologize in advance if that gives you a little bit of a headache, but we got to get through it. And so without any further ado, let's start off with Index of Hydrogen Deficiency. Talk about that. Then we'll move on to IR. That should be pretty quick because, in my opinion, IR is fairly useless. And then we'll get on to HNMR. And HNMR is particularly useful, especially when combined with IR. You know, a really good IR spectroscopists know what they're doing, and they can tease out some information. But at the end of the day, I think that most chemists are going to say, at the end, you know, by itself, unless you have access to a database of millions of previously done IR spectra, and IR spectra is not going to elucidate any particular structures other than some very specific functional groups. And we'll talk about that in a second. So let's get into it. We're starting off with Index of Hydrogen Deficiency. So what I want to do is I want to switch over to, I got to get it going, got to get it started. It's getting late. All right, here we go. Here we go. I think we got this. Okay. All right, guys. So once this screen sharing pops up, we can talk about degrees of unsaturation. Another way to describe this is the Index of Hydrogen Deficiency. What this is a measure of the lack of hydrogens a structure has compared to the same types, a similar structure with the same number of hydrogens, with the same number of carbons. And the difference is what happens when you have a certain number of carbons and they have double bonds, single bonds, triple bonds, or rings, or other sorts of structural motifs, and how does that affect this index of hydrogen deficiency, or the degrees of unsaturation? Let me give you an example. Let's just take good old propane, for example, C3H8. What happens to C3H8 if I add a double bond? It still has three carbons, but now it has 1, 2, 3, 4, 5, 6 hydrogens. It's now unsaturated. And remember, the term unsaturated just means that a carbon doesn't have the maximum number of hydrogens that it could theoretically possibly have. So the propene is unsaturated in the sense that there's two carbons. One could have 2 hydrogens, the other one could have 3, and it's just 1 and 2 in this case. So with every double bond, it seems like I'm losing 2 hydrogens. What if I made a triple bond? I've still got 3 carbons, but now I only have 4 hydrogens. So it seems to go from the double bond to a triple bond. I've lost 2 more hydrogens from the theoretical maximum. Let's take a look at something like cyclopropane, and let's think about its formula. Still 3 carbons, but again, I've got 6 hydrogens. So it seems that if I want to connect these carbons together in a ring, I also lose 2 of the maximum hydrogens that I could with 3 carbons, and make, if they had as many hydrogens as it possibly could, and have 3 carbons connected together. So what is this good for? Well, at the end of the day, we're going to give you chemistry problems that will lead you with the chemical formula. And why would we do that? Why would we lead you with the chemical formula and then have you look at IR NMR spectra? Well, the standpoint that we're going to take is that there are instruments, atomic absorption spectroscopy being one of them, that in mass spectroscopy being another one that could help elucidate what the chemical formula or the empirical formula of something is, an empirical formula and the chemical formula. So we're just going to say, look, there are ways to determine chemical formulas. And if you had an unknown compound, you could determine its empirical formula. The other thing is that really what I want you to do is be able to read NMR and IR spectra. And we've got to arm you with something if we want you to solve for the structure. If we just give you a spectra and say, what's the structure? And we don't give you any kind of clue other than the spectra, all you're going to do is you're going to come up with some possible structural motifs, but there'll be lots of different structures that will be able to satisfy those motifs that you come up with. So we give you the chemical formula in order to narrow that down to one particular version. In other words, it helps you solve problems. It helps you get problems that have solutions, right? Because there's an infinite number of problems that don't have solutions. And hopefully in a college course, you're getting problems that have solutions, unless you're in a really advanced course. And that's what they're trying to get at, is to test your brain to see how you solve problems in the first place. Just ask James T. Kirk. Ask him what he would do. I digress. Anyway, so the degrees of unsaturation help elucidate what possible structural motifs are in a particular chemical formula. And so let's get rid of the possible structures and let me write down this formula. So the index of hydrogen deficiency equals 2 times the number of carbons plus 2 plus, and I'm going to fill in some things here in just a second, the number of nitrogens plus the number of nitrogens minus the hydrogens minus the number of halogens, all divided by 2. And the way that I describe this in a lecture course is to say, we can think about the index of hydrogen deficiency as a currency that we can use to buy possible structural motifs. And what we looked at before is that if you want to have a double bond, then you need an index of hydrogen deficiency of 2. Now, if there were 2 double bonds, remember from the previous example, when we drew the structures that had 3 carbons, for each time you draw a double bond, you remove the possibility of having 2 carbons in that structure. So if you had 2 double bonds, you would need a total of, oh, I did this wrong. Somebody please play a sound of a record scratching. Let's redo this chart. There we go, motif, double bond. The IHD value will actually be 1. But what we're saying with an IHD value of 1 is that we're missing 2 hydrogens. And so it is true that between this C3H8 and this C3H6, the difference in the number of hydrogens is equal to 2. We will call this one hydrogen deficiency, one index, one IHD. So if I want a triple bond, then I would need to have 2 of those. If I want a ring, then I need to have 1. And these are the basic motifs, and if I have any combination thereof, then I'll need to add them together. So if a formula exhibits 2 double bonds, then you would expect that the calculated index of hydrogen deficiency is equal to 2. If the structure has a triple bond, then you would expect that the index of hydrogen deficiency equals 2. If the structure has a ring in it, you would expect that the index of hydrogen deficiency calculation would equal 1. If it's got a ring and a double bond, well, that means that you need 2. What about benzene? With benzene, I have 1 ring. That costs 1. I have 3 double bonds, so that costs a total of 3. So the expected calculation for the index of hydrogen deficiency for benzene should be 4. So let's actually do the calculation, and I'll show you some examples here. So I'm going to put this off into the corner just so we can remember a little bit about what's going on here. And let's start off with benzene because we just had that example. And let's go ahead and calculate the IHD. Well, it's 2 times the number of carbons, which in this case is 6, plus 2, plus the number of hydrogens, which is 0, so I'm not going to add that, minus the number of hydrogens, which is 6, minus the number of halogens, which we don't have any, so that's going to be 0. I'm not going to add that. And then we're going to take everything, we're going to divide it by 2. So what do we get? The IHD is equal to 12 plus 2 minus 6 divided by 2. And so at the end of the day, the IHD is equal to 14 minus 6. What is that? 14 minus 6. Somebody do that calculation for me. 8 divided by 2. The IHD is 4. And that's what we expect from benzene. So what happens is you don't usually get a structure. Usually you get a formula, right? And so let's do something with a formula. Let's do C3 give me a second. I want to C3H7O2. Okay, let's calculate the index of hydrogen deficiency. And I'm sorry, this would be H. This is the structure I'm thinking of. I apologize. C3H6O2. All right, so let's calculate the index of hydrogen deficiency here. Index of hydrogen deficiency. The number of carbons, 2 times 3. No nitrogens. How many hydrogens? 6. So I'm going to subtract 6. I need to add the 2. So 2 plus 3 plus 2 minus 6 divided by 2. Whoa! What about the oxygens? Well, is the oxygen in the formula? No. So I don't do anything for the formula for the oxygen. And you can see why in a second, but the presence of an oxygen doesn't affect the index of hydrogen deficiency What is affected by the presence of oxygen is what kind of bonds to the oxygen do we have. We could have single bonds to the oxygen, something like in an ether, right? The index of hydrogen deficiency here is going to be 0 because everything is saturated. But if we had an alcohol, what about this? C3HCH2OH. Again, fully saturated. IHD is going to be 0. So the IHD isn't going to help you pick between these two structures. Later on, we're going to get into NMR and IR, and that's what's going to help us pick between these two structures. IHD is just going to tell us if there's double bonds, triple bonds, or rings, or combinations thereof. But what other motifs can I have? CH3, COH. Look what happened to the formula now. I have 2 less hydrogens. In the first 2 cases, it's C2H6O. Both cases, C2H6O for both the ether and for the alcohol. But in this case, it's C2H4O. So I do have a degree of unsaturation, an index of hydrogen deficiency of 1, in order to get that double bond to the oxygen. Okay, so that's why the oxygen isn't included in the IHD calculation, because it doesn't affect it. But the bond types to oxygen do affect the index of hydrogen efficiency. So if you want a double bond to oxygen, you're going to need an IHD of 1 to do that. All right, so let's erase this bit at the bottom. Let's go back to our calculation. If you were zooming along ahead, then you calculated that the IHD is 8 minus 6, right? 2 times 3 is 6 plus 2 minus 6 divided by 2. And so that's 8 minus 6, that's 2 divided by 2, that equals 1. So that means that there's some possibilities here. With C3H6O2, I could have a double bond or a ring, but I couldn't have a triple bond because I would need an IHD of 2. And I can't have a double bond and a ring because I would need an IHD of 2. And I can't have 2 double bonds because I would need an IHD of 2. So the only possibility in this case is that I have I have either a ring structure or a double bond. So let's think about how the different rings could look out. Well, I could have C, 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 and maybe it's a peroxide. Maybe it's a 5-membered ring that has a peroxide. Let's see if this works out. Let's get everybody their full octets. Yeah, look, C3H6O2. So there's a possibility. Again, you can't determine the structure, the actual structure, unless you get more information. The IHD just tells you the possible isomers, the possible constitutional isomers of a particular formula because of the structural motifs that could be present in those constitutional isomers. So what's another possibility? I could have a ring, I could have a double bond. Well, let's think about maybe the double bond is between 2 carbons. So H, H, C, H. And then if I give everybody an octet, oh man, it's O2. Ugh, let's back this up then. So in order to get O2 without any more, boy, that's weird. I wonder what that thing is. But this would have an IHD of 1. It's not probably a very stable structure, probably doesn't exist in nature, or it's probably highly reactive, but it's a possible constitutional isomer. All it has is a double bond. Let's see, and let's throw out now one more possibility where I have a double bond to an oxygen. So it could be a carboxylic acid. This would work out, right? Here's my 6 hydrogens. This is actually the one I was thinking about in my mind. But it could also be, let me just kind of shrink this down, get a little bit more room. It could also be a weird ether and an aldehyde.
right? That would work out as well. That would be C3H6O2. And so at the end of the day, all the index of hydrogen deficiency does is elucidate possible geometric motifs in constitutional isomers. It's only when you combine the index of hydrogen deficiency with NMR, IR, IR or NMR that really you start to get into what the structure is based on the evidence that you have. Okay, so let's move on from this because we're going to use the IHD. Remember, what I'm trying to do is ultimately help you guys figure out how to do some of this NMR IR business, especially for this particular course. This video would be appropriate for the first semester Orgo Lab, where I'm at. The second semester Organic Chemistry 2 lecture, we would assume that you know this, but I'm going to post it in there anyway so that you guys can have this as review. So let's take a look at how we would do that. And let's start off with IR. IR is a spectroscopic method that takes advantage of bond vibrations. And the rule is, and we call it a selection rule, is that it interacts with permanent bond dipoles. And the electric field of an infrared light, remember that IR is electromagnetic radiation, and it's an electric field perpendicular to a magnetic field propagating in a straight line at the speed of light in a vacuum. Permanent. I'm always embarrassing myself on YouTube forgetting how to spell things. Woo, good thing I don't teach English. At any rate, permanent bond dipoles. And so the electromagnetic field will interact with, I couldn't help myself, permanent bond dipoles. They interact with the permanent bond dipoles, the electric field of light, this infrared light, and it causes the molecule to vibrate. This is what we're talking about. And it's got to be quantum mechanically matched up. And that's a conversation for advanced organic chemistry or your first semester or your undergraduate physical chemistry course or your undergraduate instrumentation course, but not second semester organic chemistry, unless you go to one of those schools just loves to pile it on for you, piled higher and deeper. So we don't go to one of those schools, so we're not going to get into it. At the end of the day, if you expose a molecule that has bonds that have permanent dipole moments, if it has a molecule that has a permanent dipole moment, then the bonds in that molecule will vibrate in particular patterns. And the patterns of vibration will absorb some of the energy in the IR light. And if you take a look at the light that passes through these molecules after it's absorbed it and compare it to the light beforehand, then you can kind of get an idea of, well, if I look at what I had before, and now I know the light that went through the sample is different, and I compare where I'm missing some of the light energy, because it'll be a spectra, then I can say, all right, and this is just one version of doing it. I can put a graph, and on the graph, I could say, well, where is the light absorbed? And all I'm showing you now is that it's absorbed in some of these locations. And for reasons that I don't actually remember, the location of where that is absorbed is an inverse wavelength. We call it wave numbers, centimeter, and the wavelength would be in centimeters. I know we've pounded it into you in general chemistry that we're going to use nanometers. But at the end of the day, you convert nanometers to centimeters to take the inverse, and then you got the wavelength. And this is what the wavelength, and remember the wavelength and the wave number. If the wavelength is inversely proportional to the wave number, then that means it's directly proportional to the energy. And so that's the energy of the absorption. And then what you have to know is that on this side of the graph, it's low wave numbers. So it's like 200 reciprocal centimeters. And over here, it's high wave numbers. something like 3,500 reciprocal centimeters. And so we're really doing a great job of being really confusing here, drawing graphs that go backwards using inverse wavelengths. Anyway, this is a hang up from back in the early 1900s when we first started doing this stuff. Those guys. Anyway, so what's the deal with IR? We'll get a spectra, and I'm going to take a look at some of the spectra. I'm going to scroll through some pictures off of Google and kind of show you what some of these things look like. But at the end of the day, what we learn is that certain bond types absorb energy at consistent wave numbers and give consistently strong or weak signals. And so here's some signals that would be strong, and here's a signal that would be weak, and maybe this one is medium. Also, I might have a signal. Let me do some erasing over here. Let's see. Let's do a signal that's both strong and broad, right? And then let's create a signal that's sort of medium and narrow, right? So this is a broad signal, and this is a narrow or sharp signal. And so those are the characteristics that you want to examine for a particular peak. You want to examine where it is in the spectra as far as wave number. You want to examine whether or not it's strong, weak, or sort of moderate or medium in strength. And that really does mean how far down in the spectrum it comes. This is an absorbance spectrum. There is a transmittance spectrum that's just the inverse of this. We start instead of starting up, we start high, and we draw peaks instead of valleys. Both are the same thing. At the end of the, I might have said that wrong. This is a transmittance spectra. Yep, I did say it wrong. Where this is 100% transmittance, and this would be 0% transmittance. So when something becomes absorbed, the transmittance goes down. My bad. The absorbance spectrum would look opposite, where you would have no absorbance and then a peak. Awesome. Anyway, let's move on. So we got to take a look at where the peak is. What is its relative strength, strong, medium, or weak? And then we have to also examine whether or not it's sharp or broad or narrow. Now, what I said before is that IR is not particularly useful unless you're really good at this. And I mean, you've got a PhD in it, or you've got access to a database that has 1 million spectra already in it, and you take a spectrum and you just hit match, and it matches one. And then it tells you, hey, this is probably what it is. And so let's take a look at this graph real quick. And I'm going to show you on a more sophisticated drawing some of the same information. We're going to look at some actual spectra. And then once we flip over to IR, I'll actually use some, and we'll examine what we have. And so let's take a look. In general, there's no information there. In general, there's no information on that side. In general, this is where all the information you get is. And so let's flip over and let's take a look at that. So here's an awesome version of a list of different IR signals as they appear on the spectrum. And so again, at the bottom of the graph, you'll have the wave numbers in reciprocal centimeters, starting with something in the 500s all the way up to something around 3,600. So again, remember I said there's this region that isn't particularly good at helping you identify things. And what's the reason for that? Look at all of the different structural motifs that overlap. And so you can, some of the things in these areas you can look for if you think that you have it, like CO stretches and bond vibrations that involve carbons and halogens. But some of the other things are not going to be particularly useful, right? So if you have something that has an oxygen in it that's connected to a carbon, and it's only connected to a carbon by single bonds, you might be able to see it, but it's going to be, it's going to be buried underneath some of these other signals. You know, maybe you'll be able to resolve it, maybe you won't. Generally, in my experience, carbon-oxygen bonds are resolvable. Some of the other bonds aren't particularly resolvable. Okay, so then if it's really kind of cluttered and it's not really good for anything, the fingerprint region, it's not particularly useful. Let's take a look at the parts. This is my opinion. Let's take a look at the parts of the IR spectra that are useful. Here's one of the first things that's really useful. One of the first things that's really useful is this. It's the CO stretch. If there's anything you do in your first part of organic chemistry, it's learning to identify the CO stretch in any IR spectrum. It's like a loud 1980s glow dye highlighter color neon sign that you just can't miss. And that's what you'll see. And we'll see that in a second. Now, let's continue to look over. Notice that it's also it's a strong signal. Notice that it's a strong signal. Okay, and so let's take a look at some of the other stuff that's in this area that's also particularly helpful. Well, look at over here in the 2200 to 2400 range. You get C triple bonds, you get carbons that have triple bonds, whether they're to other carbons or whether they're to nitrogens. And those signals are particularly easy to identify because they're the only things that really appear in this category. Even though it's a weak signal, you should still be able to see it because it's not going to be buried under other signals. It'll be apparent. Now, let's continue to move over. This magic spot in the graph is, I call it magic because if things appear to the left of this spot, then it is very telling of the different structures. And we'll get back to that in a second. But let's talk about the OH section. Take a look at this. What about OHs? What about OHs from alcohols and carboxylic acids? At the end of the day, there's one of the other things, if there's only two things that you can identify on an IR spectra, it better be the CO stretch and it better be the OH stretch. These are the two signals that any student can see after just a few minutes of practice. And so an OH stretch is both strong and broad. For an alcohol. For a carboxylic acid, it's broad, but it varies. You're not going to miss it. You're not going to miss the fact that there's a signal there, but it may not be as strong as an OH by itself. And that's because there's going to be some resonance involved with the carbonyl group as well. But what you will see if it's a carboxylic acid is a broad signal in combination with a carbonyl signal, right? Because if it's a carboxylic acid, it's a C double bond with a COH on the same carbon. And so you would see both signals in the structure. If it's just an alcohol, you won't see the C double bond O stretch, but you will see the really broad OH stretch. We'll look at some examples in just a second and I'll get an idea of what I'm talking about. So if you want to then take a look at what happens above 3000, then we can take a look at some really interesting structural motifs. So these are the only things that appear above 3000 besides the OH stretches, which are huge, right? They're huge and obvious, and so you can't miss them. But if there isn't an OH stretch and you're just looking at some other carbons and a hydrogen and maybe some nitrogens, and you have some signals that are above 3,000, then they do have some meaning. And so look at what happens with above 3,000. Here's that 3,000 line. You get some alkene stretches. So if I have a double bond and there's a hydrogen attached to a carbon that has a double bond, this is where the signal will appear. And so what has a carbon attached to a double, like for instance, aromatics, right? All the aromatic, if there's an aromatic hydrogen, it'll appear on this side of the line. Again, if you have an alkyne, and it'd have to be terminal, right? A terminal alkyne is the only type of alkyne that has a hydrogen attached to a carbon that has a triple bond. But if there were that case, then you would get a nice signal, you know, a narrow band and a strong signal right there in that, what is it, the 3,200 to 3,300 range. And it would, boom, it would be there, be obvious. The other things too are primary and secondary amines, right? And so let me just kind of draw a picture, right? A primary amine would be an amine connected to a hydrogen, R group, and it would have two hydrogens. This is primary. A secondary amine would be a similar situation, but instead of two R groups, instead of one R group, it has two. And so this is also really, really good at identifying this type of structure. So in the case of the primary amine, you get two, and I'm talking about this signal over here, this guy that's over here in this area. You get two signals. For a primary amine, it's sort of like vampire fangs. For a secondary amine, it's like one. It's like a knocked out it's only one fang. It's Gordo the vampire instead of Dracula, right? His distant second cousin. Anyway, so at the end of the day, these are the structural motifs that you'll see in IR spectra that'll be helpful for determining structure. So let's scroll through a couple of these as examples, and let's see if we can identify some structural motifs. And so what I want to do is I just want to take a look at all these different IR spectra. And so let's start over here. Let's see if we can see something. Look at this one. I'm going to open it up, and it's labeled for you. Here's this OH stretch in combination with a CO stretch. So this is that situation where you have a broad, mostly strong, and but it's not as broad as an alcohol, and we'll show you that in a second. So this is indicative of a carboxylic acid. Notice that CO stretch that's happening around 1725. That's one of the things that you just can't miss. Let's take another look at something else. Let's move through these. Here's the OH stretch. This one is for ethanol, right? This is an example of a very common broad OH stretch. And I'm looking, and I can't draw on it at this moment, but I'm looking at the left-hand side of the insert spectrum that's blown up on the website. This is the OH stretch, and it says 3391. That's where it appears, and that's where the center of it appears. Here's another version of something that's similar to that. Look, here's an obvious OH stretch. Let's take a look at some other things real quick. Let's look at this one. Here's an example of a peak that happens after 3000, where you see an alkene CH stretch. It's at 3083. So you know that since it's after 3000, it's one of those important peaks that signifies, hey, there is some important information in this IR spectra. Let's see if there's just one or two more that we can look at real quick. Let's see here. Oh, did you see this one right away? Look at that. They've highlighted, and it's in blue, they've highlighted the CO stretch. Let's take a look. Keep going. Let's look at some other ones. I'm just going to pull this one up. Looks like there's an OH stretch there. Oh, look, here's one. Here's the broad carboxylic acid in combination with the C double bond O. So you get the OH and the C double bond O in the same structure, carboxylic acid. Let's think one more. Let's see that one. So here's an example, right? This one is from Dr. Hardinger, and this is his class. And here's an example. He says, let's take this structure and let's see if we can match it up to one of these 5 different possible isomers. So let's take a look. Does it have that really broad OH stretch left of 3000? Do you see that? And I can't draw on it, but if you see to the left, right down there, there really isn't that really broad, large dip that signifies an OH. So we can get rid of cyclobutanol and 2-methyl-2-propene-1-ol. What about this thing that happens at, and you have to count it, 15, 16, 17, right about 1725. There's this really big, really long, really strong signal. What's that coming from? That's one of the ones you should identify. You should identify that as the CO double bond. And so now, not only have you identified, eliminated anything that has an OH, you've also eliminated anything that doesn't have a C double bond O. And so now we're down to 2-butanone or 2-methylpropanol. Let's take one last little moment and let's talk about ethyl vinyl ether and 2-methyl-2-propene-1-ol. Both of those things have carbons that have double bonds, and those carbons would have hydrogens. Where would those appear? So ethyl vinyl ether and 2-methyl-2-propan-1-ol would have signals left of 3000, and they'd be little stronger, not broad, they'd be narrow, sharp signals left of 3000, greater than 3000. But if you look at the spectra, there's nothing there. So those are also eliminated for that reason. Now, how do I tell the difference between 2-butanone and 2-methylpropanol? And so if we go right back and we take a look at this particular structure, what do we have? Let's look at this. One of them is an aldehyde and one of them isn't. One of the possibilities was an aldehyde and one of them isn't. So here's another example of a peak that's particularly useful. So somewhere between 2675 and 2825, we should see a medium peak. So somewhere between 2675 and 2825, we should see a medium peak. Well, let's count at the bottom. There's 2000, 21, 22, 23, 24, 25, 26, and look at that. Right between 26 and 27, there is, in the mess of those peaks, there is a peak right in that zone. And so that does indicate an aldehyde. And really, this is the spectra of 2-methylpropanol. And so that's how you would use IR. And so that's about it for IR for now. So what I want to do is I want to move into NMR. And now NMR works a little differently than IR. And this is a presentation made by one of my colleagues, Yvonne Ford, and I'm going to use it to go through it. And we'll do some practice. Okay. So NMR works similarly to IR in the sense that we're going to take a sample and we're going to bombard it with light. And it's going to react to it. In IR, it was IR light interacting with molecules that had permanent dipole moments. There's a similar situation going on here, but instead of IR light, it's radio waves. And instead of permanent dipole moments, there has to be a nuclear spin moment. Whoa, that's really, really peak hem right there for you. And so what you're looking at in this picture is you're looking at a nucleus with a vector arrow, and those vector arrows represent nuclear dipole moments. Now, not all hydrogens have nuclear dipole moments, but some of them do, hydrogens, proton NMR does, but we could do carbon NMR, but the common isotope of carbon is carbon-12. It doesn't have a nuclear dipole, a nuclear spin moment. And I keep saying dipole, but I really mean spin moment. That's really quantum mechanic-y, peak chemie. So let me back up. it's a nuclear spin moment. Protons definitely have them, but carbon-12 doesn't. However, carbon-13 does, and there's an appreciable amount of that isotope that we can still gain some information from just any random sample, because any random sample will have enough carbon-13 to develop a signal. But what we're going to do is we're specifically talking about nuclear magnetic resonance spectroscopy, that's what NMR stands for, of protons, of hydrogens. We can do carbons, we can do phosphorus, we can do nitrogen, we can do other molecules, or excuse me, other atoms, but we're going to focus on proton NMR in this video. Okay, and so I'm going to move through this presentation pretty quickly. This presentation is up there for you on Blackboard, so you can take a look at it a little bit more in depth. All right, and so I'm going to move through this. Okay, so this is where we're going to start. The first thing I want to say is that the deal with NMR is that that the signal has to have a reference. So what we're going to do is we're going to use trimethylsilane as the reference. If you take a look at all of those hydrogens attached to all of those methyl groups, you see that it's a methyl group attached to a silicon, and the silicon is attached to 3 other methyl groups. So it doesn't matter which methyl group you're looking at, that's its reality. It doesn't matter which hydrogen you're looking at, it's on a methyl group that's connected to a silicon that's connected to 3 other methyl groups. So every hydrogen is in an identical chemical environment. And so what we're going to do is we're going to use TMS to zero our scale of where signals appear. TMS will be the 0 on the scale, and we will use parts per million to describe the location on the scale. So the reason why I'm talking about this scale is because unlike IR, NMR has a really, really powerful where is the peak appearing determination of structural motifs. In the IR, there's a few signals, and where they appear does make some important determinations as to the structural possibilities, but NMR is powerful across its entire spectrum. So where the peak appears in an NMR spectrum is fundamental and important. And so let's take a look at what I mean by that. And so what I want to do is I want to swap over to a similar picture like this, and I want to be able to draw on it. So I'm going to look at it from here. So it's from the same folks, Compound Interest, as long as I'm not making any money, which of course, since I teach, I don't make any money. And I'm not going to monetize these videos because they're for students. Not that I could anyway, because nobody would pay to watch me. Let's take a look at this chart. Okay, now when we look at this parts per million business, this is what I want to remind you of. Here's the peak that TMS, trimethylsilane, this is where it appears at 0 parts per million. Everything else will be scaled based on a shift from that point. So what the NMR does is it goes along and it finds this TMS signal, and it then says, okay, there's my 0 point. And then it says, how far shifted in parts per million is any signal coming from my sample going to be? And so let's take a look at the different functional groups. Now, to the right, there are some, it's busy, right? There are lots of overlapping signals. But what should we get from this particular bit of information? It's right here. And right here. It's in this 1 to 2 parts per million range. All of the, and again, it's up here as well. all of the tertiary, secondary, and primary alkyl hydrogens will appear in this range, as well as allylic hydrogens. And it's not vibrations, it's not bins, it's not stretches like it was in IR. Remember, it's nuclear spin moments. And so we're going to say these are where the signals develop. And now you can go and talk to somebody in physics, or you can go to PChem and you can talk about a free induction decay and doing a Fourier transform, not in organic chemistry. We're not going to do that. So there are some other signals that are in this territory that are particularly helpful. You can see that where a particular motif appears isn't necessarily shared by a lot of different things. So for instance, the ketone would only overlap with benzylic hydrogens. So if something appears right here in the 2 to 2.5 region, or a little bit over 2.5, in the 2 to 2.5 parts per million, then you're pretty sure that it's going to be a ketone, a hydrogen attached to a carbon directly adjacent to a C double bond O, or it's going to be a benzylic hydrogen. And so unlike IR, this section of the graph is still pretty helpful for what kind of structures are present in the molecule. Let's take a look further down the chart, further downfield into greater parts per million, greater chemical shifts. Look what happens. Things really start to get uncluttered. In the 4.5 to 6 part per million range, there's a few things listed. But once you get past 6.0 parts per million, there's not a lot of things going on. And the things that are going on are very unique. So for instance, a phenolic hydrogen, there's only one possibility for that, right? It has to be an OH on a benzene, and it has to be that hydrogen, right? And so what else do we have here? Amide. Remember, amides are very particular structures. Carbon doubly bound to an oxygen, connected to a nitrogen, and then that nitrogen would have to have a hydrogen on it. And then that's where the signal would appear. So that's very specific in its structure. If it's aromatic, right, it's in this range. So in other words, if something appears from 7 to 8.5 parts per million, there's only two possibilities. It's either aromatic or it's an amide. And if it doesn't have a nitrogen in it, then it's got to be aromatic, right? It's got to be a hydrogen that's attached to an aromatic ring. That's what it has to be. Now, let's look further, a little further. Wow, there's nothing going on down here except for aldehydes and carboxylic acids. There's a little bit of overlap between aldehydes and carboxylic acids, but essentially after 10.5 parts per million, the only thing that can appear down here from 10.5 to 13 parts per million is a hydrogen associated with a carboxylic acid. The only thing that it can appear between 9.5 and 10 parts per million is the hydrogen of an aldehyde. It's only in this regime that there could possibly be any confusion. And so this is why where the signal is in NMR is really, really powerful. Okay, so what we've talked about so far is what NMR is and where the signal is, but there's other aspects to an NMR spectrum, and we need to get to that too. Okay, so let's take a look. Let's go into where the signal is. So I'm showing you the actual structure. It's an ester. So all of the hydrogens are connected to carbons, and then those carbons are connected to other things. And so what do we have then? We have a signal that's at 2 parts per million and a signal that's at, so there's one there, and a signal that's at about 3.7 parts per million. Let's go back and match that up with our previous. So again, just to remind myself, because I have a short attention span, it's around 2.1 parts per million, a little bit less, and about 3.7. So let's take a look. What's 2.1? Oh. Is it a carbon connected to a carbon connected to a double bond? Let's go back and look. Is it a carbon connected to a carbon connected to a doubly bound oxygen? Yeah, there we go. So this one is probably the 2 ppm signal. What about these hydrogens? And I should really point. I really should point. Really should point to the hydrogens. And so what about the other one? Let's go and take a look at that one. So it was about 3.7. So that's about right here. A carbon that's connected to an oxygen. Is that where it shows up? Yeah, look. It's a carbon connected to an oxygen. So this is probably the signal at 3.7 ppm. And so again, I'm hoping that I'm illustrating how powerful the location of the signal actually can be. So let's take a look real quick. All right, we've discussed where the signal is. Now, here's the other part. The number of signals is exactly the same as the number of equivalent hydrogens. And so let's go back to TMS real quick. Remember that I said that each hydrogen in TMS is in the same chemical environment. It's in a unique chemical environment. And so there's only going to be one signal because it's a hydrogen connected to a carbon, and that carbon is connected to a silicon that's connected to 3 other methyl groups. And it doesn't matter which hydrogen you're looking at, it's all the same. Okay, and so let's take a look at this. So we're talking about chemical environments. And so it's saying each of these molecules will have only one signal. Propanone, it's a CH3, C double bond O, CH3. It's perfectly symmetrical. The hydrogens on either side of the C double bond O are in the same chemical environment. 1,2-dichloroethane, so a chlorine on both carbons in an ethyl group. So that means that the hydrogens in there are all connected in the same chemical environment. Cyclopentane, CH2, 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 CH2 in a ring. They're all in the same chemical environment. 2,3-dimethylbutene. So 2,3-dimethyl-2-butene has a very symmetrical structure. So all of the hydrogens that are in this structure will end up giving the same signal. Make sure I can use my pen here. Yeah, there it is. These are all giving the same signal because they're all in the same chemical environment. Okay, let's take a look at these. If we have 2 or more unique chemical environments, then we'll get 2 or more signals. So let's take a look. In 1,1-dichloroethane, you've got CH3 connected to a carbon, and that carbon is connected to 2 chlorines. So this hydrogen is in a different chemical environment than those 3 hydrogens, so you should see 2 signals. The same thing's going on here. These 2 hydrogens are 1 removed from the C double bond O. These 2 are 2 removed, so it's a different chemical environment. Now, remember that there is no free rotation around a double bond. So that means that, well, let's say, for instance, let's change this. If there was a hydrogen here, that would mean that this hydrogen and this hydrogen are in different chemical environments. But I got ahead of myself. There isn't a hydrogen there, it's a chlorine. And so I'm thinking about this hydrogen, and this hydrogen. They're all three in different chemical environments, so you'll get three different signals. Let's take a look at this guy. Hydrogens here. I've got two hydrogens in both of these locations, two in there. You see that these hydrogens are in a different chemical environment than these hydrogens, which are a different chemical environment than the hydrogens far away from the double bond. So that's three signals. So let's continue on and take a look. Here is a molecule. I'm going to draw it out just a little bit more specifically. CH3, C double bond O, O, C, CH3, CH3, CH3. These hydrogens are all in the same chemical environment because there's free rotation around that double bond, or that single bond, that averages them all out. These hydrogens are in a completely different chemical environment. So there's two signals here. Okay, two signals here. Again, take a look. Here's that ketone signal. And here's that ether signal. Again, the location is important. All right. Now, let's get a little deeper into the signals. So there's a lot going on here. I know this video is going to end up being long, but we got to keep pushing through. Pause and take a break if you need to. We've talked about where the signal is. That's important. We talked about how many signals there are. That's important. Now we want to talk about is the area under the curve of each signal. And so if you take a look at these signals, I've done some measuring the area under the curve, and I've measured it as 67 in the arbitrary units here to 23. What I've done is I've taken that and I've turned it into almost the lowest whole number ratio, and then in the last case I did round it to the lowest whole number ratio of hydrogens. The relative area of each peak is proportional to the number of hydrogens giving that signal. So if I were to just come back here and look at the structure, erase this bit. If I were to come back and look at the structure, I would say I've got all of these hydrogens are the same, and there's 9 of them. All of these hydrogens are the same, and there's 3 of them. So the signal ratio should be 3 to 9, and then we would reduce that to its lowest whole number ratio, so it's 1 to 3. And of course, I've just reversed it. It's the same ratio, right? So when we look at an IR spectrum, it's going to give you, or you can measure, the relative area of the peaks and establish the lowest whole number ratio to determine the proportionality between the number of hydrogens giving that signal and the peak area. So again, this is really important as far as being part of the signal. Okay, so let's take a look. So we've talked about where it is. We've talked about where it is. We've talked about how many there are. We've talked about the relative area under the curve being proportional to the number of hydrogens. And now we want to talk about yet another property of signals. It's how does the signal split? And by splitting, I mean the ideal signal is just a single peak. But that signal could split into two very close peaks that are right next to each other, centered around the same ppm, And we would say that this is a splitting pattern. Now, if I were to actually draw it correctly, I would want it to have essentially the same total area as the peak before. And this would be what we'd say the splitting here is a doublet. It could split into a triplet. It could split into, and I want to draw this doublet a little bit better. It would be something like this. Okay. It could be a quartet. Could be a pentet. See how that split into 5, and so on and so forth. We can keep drawing these splitting patterns. Okay. Whew, the splitting is the hard part. What does splitting mean? Okay. An NMR signal is coupled to hydrogens on adjacent carbons in a way that it causes the ideal signal of one single peak to split into a different pattern based on the number of hydrogens on that adjacent carbon. And the rule is the N+1 rule. And so let's take a look, right? Let's draw a molecule. And what I want to do is I want to draw, I really want to make sure I'm doing it right. CH3, CH2, CH3. Here we go. Let's identify the number of peaks, right? This CH3 and this CH3 are the same. So they're going to be one peak. And then this CH3, this CH2 is different. It's a different chemical environment, so it's going to be its own peak. Where are they going to be located? Remember, this is just single bonded carbons, so they're going to be around that 1.5 range, 1 to 1.5 range. That's where they'll all appear. What will the integration pattern look like? Well, how many total hydrogens is it? It's 6 to 2. Right? Because I'm counting all 6 of the yellow ones. So that comes down to 3 to 1. That will be the integration pattern. Now let's think about the splitting, right? Let's take a look at the splitting. What we're saying is that the hydrogens that are giving this signal will be split by those hydrogens. And then accordingly, the hydrogens giving this signal will be split by those hydrogens. And the splitting pattern of the signal will be based on the number of hydrogens on the adjacent carbon. And so follow me along here. How will this one be split? Well, how many are adjacent to it? There's 2. 2 plus 1 equals 3. So this signal for the 6 hydrogens should be a triplet. The signal for the 2 hydrogens are split by how many? Well, they're split by 6. So the signal for those should be a, let me erase some space, should be a septet. So 1, 2, 3, 4, 5, 6, 7. That's a septet. Whoa! This part is tough and it takes some practice, and we'll go through a couple here in just a second. So we'll do some examples right now. Let's take a look. So let's look at this next slide. All right, so here's an example. It's CH3, CH, Cl2. So there's 2 peaks, right? They got two unique hydrogens. I've got this one and I've got these. All right, so you'll see that that this hydrogen is over here and that these hydrogens are over there. And that bears out from the relative size of the peak areas. This peak area over here is much larger than the one on the left. And you can go back to the chart and you can see that this hydrogen should appear around 5.9. And so let's take a look at what they should split like. Okay. These three will be split by the hydrogens on this carbon, and there's one hydrogen on that carbon, so it's N+1. It should be a doublet. Ah, there it is. This hydrogen should be split by the hydrogens on this carbon. And there's three of them. 3 + 1 is 4, so it should be a quartet. That's how it works. Let's do some more examples. Oh, whoa, let's see. Slideshow from current. Aha, okay. So now, pretend you didn't see any of the answers. Let's predict the number of signals, the splitting pattern, and the integration pattern. So this is where I want to go with this. And so we're getting really close to the end. And so this is the last part of the slideshow that I want to get to. And then I'll do one example on the lab, and then we'll wrap it up for the day. So let's take a look. How many signals, what would the splitting pattern be, and what would the integration pattern be? And then you can go back to the chart and you could think about where you would predict the signals to appear as far as parts per million, right? So let's take a look. How many unique hydrogens are in this molecule? I'm trying to use a laser pointer or something. Whoa, what do we got here? All right. Okay. These hydrogens are different than these hydrogens, which are different than those hydrogens. So there should be 3 signals. Hopefully you see that. What would the integration pattern be? What would I expect the different integration areas to be, the areas under the curve? Well, it should. How many hydrogens is this? This one's 3, this one's 2, and this one's 3. And 3 to 2 to 3 is the lowest whole number area ratio. Not only can we know the actual areas under these curves, but we should be able to predict what the splitting pattern of each area is too. Let's go do that. So how would this one be split? What would the splitting pattern be? Would the signal be a singlet, a doublet, a triplet, etc.? Well, let's take a look. We look on the carbon next to it and we count the number of hydrogens that are there. None. N+0 is 1, so it should be a singlet. What about this one? What should this one be? Again, we're going to count the number of hydrogens. It's 3 next to it. So 3 + 1 is 4. This one should be a quartet. What about this one? We're going to count the number of hydrogens next to it. It's 2. So it should be a triplet. So again, what do we know about the NMR spectra? The NMR spectra should have 3 signals. The integration pattern should be 3 to 2 to 3. We also can pretty accurately predict where they're going to appear in the spectrum. I'm going to let you go back and look at that chart. We also know that one of the areas under the curve that integrates to a whole number ratio of 3 will be a singlet. The other one will be a triplet. And the one that integrated to a whole number ratio of 2 will end up being a quartet. And so we can do that with each one of these other ones. And I'm gonna go over to the last one. You should pause the video real quick and try to work this one out on your own. Seriously, pause it. Okay, great. Welcome back. All right, so now how many different hydrogens do we have? Well, this one is a unique hydrogen. This one is definitely a unique hydrogen. Well, what about these two? Are they unique? Are they the same, or are they each one of them different? Well, remember, because of the free rotation around this bond, these two end up averaging out. So again, what's the connectivity? Hydrogen's connected to a carbon that's connected to a carbon, talking about this one now, and that carbon is connected to a hydrogen, a methyl group, and the C double bond O CH3. It doesn't matter if you're talking about these hydrogens or these hydrogens, they have the same connectivity environment, so they're the same chemical environment. So we should see 3 unique signals. And they should integrate how? This one should integrate as a 3, this one should integrate as a 1, and this one should integrate as a 6. So it should be 6 to 3 to 1. Now, what do we have? Let's do splitting. What would the splitting of this one on the left be? Again, looking over to this carbon, there's no hydrogens, so 1 plus 0, this one should be a singlet. What about this hydrogen? Well, I'm going to count all 6 of these hydrogens because it's, even though they're on 2 different carbons, remember they're equivalent carbons, so there's a total of 6 adjacent hydrogens. So this one would be a septet. What about this one? Well, there's only 1 hydrogen next to it, so it should be a doublet. Okay, so pause the video, do the one on B, and let's see if you get it right. All right, there's all the answers. And this is, the first 2 certainly match up to what we have. The third one matched up to what we had, or the first and third. Did the second one match up to what you predicted? I hope so. Okay, there's one other thing that I need to kind of get at. I need to get at this idea about complex splitting patterns. And so there's a situation that can occur if you're come out wherever you are. All right, I'm going to ignore it for now. What about this situation? Let's specifically look at, I'm going to try to, let's specifically look at this set. What would the splitting pattern here be? Well, this is a unique set of hydrogens, but so is this one. And so there's this situation where what happens if you have neighboring carbons that both have unique hydrogens, and they're not the same unique hydrogens. Then what we get is this situation, what we call complex splitting. And with complex splitting, in this course, in this level, at this particular school, we're not going to talk about what's the possibilities. And so in this case, what are we looking at? If I just looked at this one, I would say quartet. If I just looked at this one, I would say doublet. So what do we get? Do we actually get a quartet that splits again into a doublet, or a doublet that splits again into a quartet? Well, it turns out it depends on something called the coupling constants, and you can figure that out, but I'm not going to make you do that. Maybe you go to one of those schools that does make you do that, and that's just too bad for you because your professor's mean. Maybe. But again, you have to look at the coupling constant, and whatever coupling constant is stronger will determine the splitting pattern. So what if you run into a situation like this? You're going to call it complex splitting. That's really all you should look at. And then you'll see a signal, and let's go back to it. Look, here's some signals that have some complex splitting patterns. They're not clearly doublets or quartets or whatever. How do we not look at this one? It's a quartet, doublet, something like that. Okay, and so I'm going to leave the presentation like that, and let's do one practice problem. Let's do one practice problem, and I'm going to let you guys go from there. So I'm looking in this lab manual, and I'm trying to put it all together. And so this is the NMR lab that's in the lab manual, and I want to start with this one. And so let's try to put everything together. So let's do the first thing, and the first thing, remember, is to calculate the index of hydrogen deficiency. So if I go back to this one, let's see. Where was it? There it is. What's the index of hydrogen deficiency? Well, it's got 3 carbons, so it's 2 times 3 minus 2. What's the rest of that formula? How does that work out? It does have nitrogens in this case, so I want to add the nitrogen, so that's plus 1. And there's no halogens, so I'm done there. And now what I want to do is divide by 2. So 6 minus 2 is 4. And oh, I didn't count the number of hydrogens. How many hydrogens are there? I got to do that too. So let's redo this. Sorry, let's redo this. Okay. 2 times the number of carbons, which is 3, plus 2, plus the number of nitrogens, minus the number of hydrogens, and the number of hydrogens is 9. There we go. I did it. There we go. Divided by 2. All right. And so now what do I get? At the end of the day, I get 6 plus 2 is 8, plus 1 is 9, minus 9 is 0. 0 divided by 2 is 0. So the index of hydrogen deficiency tells me that whatever this structure is, there's no double bonds, there's no rings, there's no triple bonds. Okay, let's look at the IR. Let's see if there's some structural information that's particularly helpful to look at. I don't have any oxygens in it, so I wouldn't expect to see big peaks. Let me go back and show you real quick. We saw, oh, there, look at that. Big peak here, probably a carboxylic acid. What else do we have? Oh, look at this big peak here. That must be an OH. So do you see how you can easily identify some of these common peaks? Let's take a look at this one again. Look at this spot. Here's my 3000. I do have some vampire fangs at above 3000. What do the vampire fangs mean again? They mean primary amine. And so I probably have an N, I definitely have an N that has 2 hydrogens attached to it. Okay, well, what's my formula? C3H9. So what are the possibilities? So what is this R group? Let's think. I can think of 1, 2, 3. That possibility, that matches up, but so does this one. Those are the 2 possibilities that match up with us. And so let's take a look at these 2 possibilities and let's think about how that lines up on our NMR spectra. Again, I'm going to write them down again. NH2 versus NH2. Well, let's look at these and let's think about how many unique hydrogens there would be. Well, I'd have 1, 2, 3 hydrogens here, 2 here, 2 here, and then I've got these 2. In this case, I've got a CH3, a CH3. Looks like there's 1 hydrogen there, and then I've got these hydrogens. How many signals would each one of these develop? Let's take a look at this one. We'll look at the symmetry in this molecule. That means that these hydrogens are the same. So then if they're the same, how many signals would I get? I would get this one, and then I'd get the signal for both of these. And what would the integration pattern be? 2 to 1 to 6. Let's look at this one. That's different than that, which is different than that, which is different than that. So it looks like I would have 4. I'd have this one, I'd have this one, I'd have this one, and I'd have that one. And so this would be 3 to 2 to 2 to 1. Well, look what we actually have. We have 6 to 2 to 1. So it looks like we figured out what our structure is. Let's just verify splitting and then we'll be done. Okay. The 6 would get split by this hydrogen. So the 6 should be a doublet. 1 plus 1 is 2. What should this one be? Now, here's a little secret. Hydrogens on heteroatoms do not split, nor do they become split. So what does that mean? That means we don't even have to look. This should be a singlet, because those 2 hydrogens will not become split, nor do they do any splitting. So you might be tempted to say, oh, it's going to be complex because I've got unique hydrogens on 2 neighbors. But remember, since one of them is a nitrogen, a heteroatom, they don't do any splitting, nor do they become split. So really, I'm just dealing with 7. So this one should be a septet. And this is what I have: a septet, a singlet, and this one ends up being the doublet. Okay, it's a lot of work. I know it. It's a lot of work for me. It's going to be a lot of work for you. What you should do is you should go through this lab, do a bunch of these practice exercises, calculate the IHD, get what information you can get from the IR, propose some possible structures, and then see what you can do with the NMR and see if you can eliminate or validate some of those possible structures. If you have any questions, you know how to get a hold of me. Whew, long video. This is enough for today. Good luck on NMR and IR.